Welcome. The topic we will be discussing in this lecture is multi-threading and chip multiprocessors. So we are discussing about parallel processing. In the last lecture, we have discussed about MESI protocol, which is a part of cache coherence. Before that, we have discussed about symmetric multiprocessor. In symmetric multiprocessor, you are supposed to use cache so that the bus utilization will be minimized. But when you use cache, it leads to a problem called cache coherence problem, and how to deal with the cache coherence problem, and the different approaches we have discussed. But the one which we have discussed in detail is MESI protocol. So in today's lecture, we will be moving to the topic multi-threading and chip multiprocessors. So basically, here we will be discussing about different types of multi-threading with respect to parallel processing. So we have discussed about multi-threading in operating system. There, our assumption is a uniprocessing system, a system with a single processor. But now here we are going to discuss multi-threading in a parallel processing environment. The performance of a computer, the performance of a processor, the performance of a processor is measured by the number of instructions it executes in a unit time. The processor performance is measured by the rate at which it executes instructions. That is, in a given time, how many instructions it executes. Based on that, the performance of a processor is measured. And it can be given like this: MIPS rate. The MIPS stands for millions of instructions. Millions of instructions per second. Okay, million instructions per second, or you can say million instructions per second. Rate is equal to F into IPC. Well, F is the clock frequency of the processor in megahertz, and IPC is the average instructions per cycle. IPC stands for instruction per cycle. So it is an average. At an average, how many instructions will be executed per cycle. So generally there are two ways to increase the performance. The first is the performance can be increased by increasing the clock frequency and by increasing the instructions that complete during a cycle. So these are the two general ways of improving the performance. We have discussed about this in the very first lecture of the course itself. If you remember, we have discussed about clock frequency and clock rate, all these things. Okay, there we have discussed that the performance of the processor can be increased by increasing the clock frequency. But this is little misleading. You see, sometimes the company like Intel or AMD, they may increase the clock frequency, but the number of instructions executed per clock frequency may not be, maybe there may not be any there may not be any change with respect to that. Say for example, previously previously the processor is executing say 1000 instructions per cycle. 1000 instructions per cycle. Okay, say the clock frequency is something, say some megahertz. Okay, 800 megahertz or 900 megahertz. Now the company is saying that, now the organization is saying that we have doubled the clock frequency. It is now the clock frequency, previously it is 800 megahertz, now it is 1.6 gigahertz. But previously with 800 megahertz clock, in one clock cycle, it is executing how many instructions? 1000 instructions. Okay, now say for example the clock frequency is 1.6 gigahertz. Okay, but within 1.6 gigahertz, if it is executing only 500 instructions, then there is no improvement at all. Okay, So clock frequency increasing means the duration of the cycle will be decreasing. Okay, say for example, if this is the clock frequency, okay, frequency is 1 by time, right? So if this for this time, if the frequency is, okay, if the frequency is what, say 800 megahertz, 800 megahertz, okay. Now if you say that we have improved the clock frequency to 1.6 gigahertz, then it means what? Then one clock cycle will complete by this time itself. It won't take that much time now. So that is what is called as improving the clock frequency. Previously, one clock was taking this much time. Okay, so there will be some time value for this that you can calculate by 1 by 800 megahertz. Okay, so this is previously this is T naught. Okay, or whatever it may be. Now this time is T1. Okay, T1, where T1 is equal to T naught by 2. Okay, where T1 is equal to what? T naught by 2. So improving the clock frequency means what? This duration will be reduced. Okay, this duration will be reduced. Okay, so it is not just enough to increase the clock frequency. So when you increase the clock frequency, then appropriately the instructions executed during that clock frequency also should remain same. So previously, for example, in one clock cycle, the system is executing 1000 instructions, and now also after improving the clock frequency, also if it is executing 1000 instructions, then it is a real improvement. Okay, after improving the clock frequency 1.26 gigahertz, now also if it is executing 1000 instructions within 1.6 gigahertz, then it is really an improvement. Because previously it takes 800 megahertz clock cycle to execute 1000 instructions, but now it is executing 1000 instructions within 1.6 gigahertz clock duration, and the clock duration for 800 megahertz will be larger, or it will be double as that of the clock duration of 1.6 gigahertz. Okay, right? Improving the performance can be either by increasing the clock frequency or by increasing the number of instructions that complete during a cycle. Okay, right. And what is multi-threading? So multi-threading allows high degree of instruction level parallelism without increasing the circuit complexity or power consumption. Okay, but see, so ultimately what we want to do, we want to improve the performance of the processor. So for improving the performance of the processor, if you improve the clock frequency, or if you want to increase the number of instructions that can be executed during a clock cycle, if you want to do all these things, then the complexity of the circuit of the processor will increase, and the power consumption may also increase. Okay. So is there any other way to improve the performance of the processor without increasing the circuit complexity and without increasing the power consumption? Is there any other way? Yes. So there is a way by using a technique called multi-threading. So with multi-threading allows for a high degree of instructional level parallelism. Okay. So what is instruction level parallelism? Instruction level parallelism is a concept which is connected with threads. Okay, instruction stream is divided into several smaller streams known as thread. Generally, instructions are coming from a process. What is a process? A process is a program under execution. Okay, and a given process can be divided into several small threads. Okay, threads are otherwise called as lightweight processes. Threads are otherwise called as lightweight processes. So this is how we define thread in operating system. But there is another way of defining threads. Instruction stream. Okay, instruction stream means what? Stream of instructions, flow of instructions which is coming is divided into several small streams known as threads. Okay, so it is something like you are getting some stream of instructions. Okay, the processor is getting stream of instructions, but those stream of instructions are divided into several smaller streams. Okay, so the processor is getting stream of instructions. If these stream of instructions are divided into several smaller streams, then these individual smaller streams are called as what? Threads. Okay. So this is how here we define thread. Okay, the actual meaning is same, right? So what is meant by instruction level parallelism? Let me define that also. So instruction level parallelism means, see, a process is a program under execution. A process has an instruction stream, and this instruction stream is divided into several smaller streams. These smaller streams are called as threads. Okay. So process is having a, what you call, it is having a instruction stream. Okay. And the instruction stream from the process is divided into several smaller streams. These smaller streams are called as threads. Like a process may have several threads, thread 1, thread 2, thread 3, so on and so forth. Okay, it may have several number of threads. Okay. Now if you take each thread is what? Each thread is a set of statements. In one thread itself there may be multiple statements. Okay, in thread 1 there will be multiple statements. In thread 2 there will be multiple statements. In thread 3 there will be multiple statements. Like that, every thread is nothing but a set of statements. Okay. Every thread, each and every thread is nothing but a set of statements. Okay. So thread 4 is a set of statements. Okay. So like that, all threads are nothing but set of statements. Okay. Right. So if you take one thread, in this one thread itself, there may be different instructions. Okay. And these different instructions can be executed simultaneously. That is called as instruction level parallelism. So the parallelism means what? Executing things simultaneously. Okay. How we are going to execute simultaneously, that we will discuss. See, we are not only here talking about concurrency, we are also talking about parallelism. Concurrency means context switching. There is only one processor. That processor is context switching from one thread to another thread. That is called as what? Concurrency. So processor initially executes thread 1 for some duration, and then it executes thread 2 for some other time, then it executes thread 3 for some other time duration, then it executes thread 4 for some other duration. That is called as what? Context switching. But here we are calling instruction level parallelism. Parallelism means, say I have only one processor. The processor is one only, but inside this processor there is a pipeline, right? So let us say the processor uses 4-stage pipeline as usual. The fetch unit, decode unit, execution unit, and write unit. But consider that this processor is having 2 execution unit or 3 execution unit. Okay, there are 3 execution units inside the same processor: E1, E2, and E3. It means what? It can execute 3 instructions at the same time. There is only, let us assume there is only one fetch unit, one decode unit, and one write unit. But there are 3 execution units. It means what? It can execute 3 instructions parallelly. Which means, assume currently processor is executing thread 1. Then it is not that it can execute only one instruction of thread 1. Because we have 3 execution units. The processor can execute 3 instructions of thread 1 at the same time, provided this instruction does not have any data dependency. Okay, provided one instruction does not depend on another instructions, then 3 instructions can be executed simultaneously. Okay, even though we have only a single processor. So this is called as what? Instruction level parallelism. Instruction level parallelism. Okay, so instruction level parallelism means, in a given thread, the ability to execute multiple instructions of a given thread simultaneously. This is the definition. Okay, the ability to execute multiple instructions of a given thread simultaneously. That is called as instruction level parallelism. So it can be achieved with a single processor also. Okay, of course it can be achieved with multiple processors also. If you have more than one processing unit, then also it is possible, right? So from a given thread, you give different instructions to different processor. Let it execute. Okay, that is also comes under instruction level parallelism. Okay, fine. So here let us define threads and process more officially. Okay. So thread in multi-threaded processes, may or may not be same as the concept of software threads in operating system. It may or may not same means what? In some cases it is same, but in some other cases it is not same. Okay, so you cannot say it is exactly same as that of operating system, but mostly it is similar. At few places there are some differences. Okay, right? So thread is concerned with only scheduling and execution. Thread is concerned with only scheduling and execution. See, the definition of process is same. Process is a program under execution. Okay. Thread is a lightweight process, or according to our textbook, we can define thread as what? Uh, there is a stream of instructions, and this stream of instructions can be divided into several smaller streams. These smaller streams can be called as threads. Okay, right. So the thread is concerned with only scheduling and execution, scheduling the thread and execution of threads, whereas process is concerned with scheduling, execution, and ownership. Okay, process is concerned with scheduling, execution, and ownership. So there is one extra thing here with respect to process, that is called as ownership. With the thread, there is only scheduling and execution. There is no ownership. Why is that? Because a process owns the thread. Okay, a process owns the thread. A process owns the thread. Threads belong to whom? Threads belong to process. That's it. But threads does not own anything. Okay. So does threads own something? Nothing. Okay. So there may be more than one process. It is not that only one process. Process 1, process 0. Like that there may be multiple processes. This is say process 0. This may have some threads. And there is process 2. This may have some threads. Okay. So now the now the system may context switch from process to process. Say for example, the operating system first executes process 0 for say 10 milliseconds. Okay. Then another next 10 milliseconds it executes process 1. Then for next 10 milliseconds it executes process 2. Okay. Right. Now when process 0 is executing for the first 10 milliseconds, here say there are 3 threads, thread 1, thread 2, and thread 3. Then this process 0 may divide some time like 3 milliseconds for thread 1, 3 milliseconds for thread 2, 3 milliseconds for thread 3, because it has only 10 milliseconds. So it will execute 3 milliseconds for thread 1, 3 milliseconds thread 2, and next 3 milliseconds it will execute thread 3. Okay. Now context switching from one thread to another thread will be done by the process itself. When there is a context switch from one thread to T1 to T2 or T2 to T3 or again from T3 to T1, all these things can be taken care by this process 0 itself. Okay. But context switching from one process to another process will be taken care by operating system. Right? So context switching from one process to another process is actually a costly operation. But context switching from one thread to another thread is not a costly operation, it's a simple operation. Because process owns the thread. And who owns the process? Operating system owns the processes. Threads does not own anything. So there is no ownership for threads. There is ownership for process only. Okay. A process is an instance of program running on a computer. There are two key characteristics of a process. One is ownership, another one is scheduling and execution. Okay. So the operating system switches the control from one process to another process by saving the details of the process in the stack. Okay. Every process will have some process status, right? The process status includes the contents of its registers and all other information. Everything will be saved. into the stack, and then only it can take another process, right? Thread is a dispatchable unit of a work within a process. Okay, so thread is a dispatchable unit of work within a process. This is another definition of thread. So we got three definitions of thread. Thread is a lightweight process. That is our original old definition. Okay, and here what we have discussed, thread is so so instruction stream is divided into several smaller streams. These smaller streams are called as threads. Here there is another definition. A thread is a dispatchable unit of work within a process. Okay, that means a process can have more dispatchable unit of works. If a process has three dispatchable unit of work, I mean which can be considered as three different works, then each of these three dispatchable works can be called as a thread. Okay, so each one is a dispatchable work. So where each of one can be called as a threads. Okay, D1, D2, D3 I am calling as dispatchable units. Okay, right. So each thread includes processor context. I mean like which processor it belongs. Okay, and each thread also will have its own each thread will have its own program counter and stack pointer. Because thread also what, see this is a thread T1 means thread contains what set of statements. So after executing one statement, it should execute next statement. So how the control will go through the program counter. So it will have its own program counter and stack, right? Because within thread also, within process also, we are going to switch from one thread to another thread. So when you switch from one thread to another thread, this thread status should be stored. So where it will be stored? It will be stored in some stack. So there may be some small stack area for every process. There it will be stored. Okay. Right? And it executes sequentially and is interruptible so that the processor can turn to another thread. Okay. So normally threads execute sequentially, but the process can interrupt it. This thread belongs to this process means it can interrupt it and it can stop it and it can switch to another thread. Okay, right? So all these things are very similar to what we have discussed in operating system. There is not much difference. The act of switching processor control between threads within the same process is called as thread switch. Thread switch means what? The act of switching the processor control. The act of switching the processor control within the same process, but within different threads. The act of switching the processor control between different threads of the same process is called the thread switch. It is a less cost operation when compared with process switch. Okay, process switch is what? Operation that switches the processor from one process to another. That is called as process switch. Okay, that is the processor is switching the control from one process to another process. It is a costly operation, whereas thread switch is not a costly operation. It's a less cost operation. Okay, so this is a brief intro about threads. And next, threads can be broadly classified into two categories. Threads can be broadly classified into two categories. One is called as explicit thread and the other one is called as implicit thread. Okay, so we are going to discuss in detail about explicit multi-threading. Okay, so what is explicit thread multi-threading? Before that, there are two types of threads. Before let us discuss about implicit and explicit thread multi-threading, let us understand there are two types of thread. One is called as user threads. One is called as user threads and the other one is called as kernel threads. One is called as user threads, the other one is called as kernel threads. Okay, the user threads are the threads which are created by the user applications. The threads that were created by the user applications are called as user threads. And the threads that were created by the operating system kernel is called as kernel threads. The threads that were created by the user applications are called as user threads. And the threads that were created by the operating system kernel are called as kernel threads. Okay. So generally these user threads and kernel threads will be known to the processor. Like these are the user threads and these are the kernel threads. Okay. So these threads are called as explicit threads. These threads are called as explicit threads. Okay. Right. So here what happens in the sense. So explicit multi-threading means the processor can concurrently execute instructions from different explicit threads. The processor can concurrently. Concurrency means it is not parallelism. Please remember, it is context switching. Okay. So the processor can concurrently execute instructions from different explicit threads. Say there are two user threads, say U1, U2, and two kernel threads, say T1, T2. So it means what, these threads are not belonging to the same process. These threads are belonging to different process. Okay. Say maybe U1 maybe belong to some user process P1. Okay. Right. U2 may belong to some user process P2. Both, but they are threads. Okay. And T1 may belong to some kernel process K1, and T2 may belong to some other kernel process K2. Okay. Now, if the processor is switching between these threads, then such an multi-threading is called as explicit multi-threading. That is, the processor concurrently executes instructions from different explicit threads. Repeating. So, first few milliseconds it is executing threads belonging to P1, then it is executing threads belonging to P2, then it is executing threads belonging to K1, and then it is executing threads belonging to K2. So, that is called as explicit multi-threading. Okay, right? Whereas in implicit multi-threading is a concurrent execution of multiple threads extracted from a single program. Okay, it's a concurrent execution of multiple threads extracted from a single program. So here, what does it mean? It means that actually there is only one program. So in this program there are different threads. There are different threads like T1, T2, T3 and T4. Okay, T1, T2, T3 and T4. Okay, and now the processor is executing T1 for sometimes, T2 for sometimes, T3 for sometimes, and T4 for sometimes. So this type of multi-threading is called as implicit multi-threading. Okay, so normally we discuss implicit multi-threading in operating system course. In operating system course, the type of multi-threading we discussed is implicit multi-threading, because there the processor is switching only from processor. I mean, the processor is aware. The processor is consciously switching, or the operating system makes the processor. So this is the processor. Operating system makes the processor to consciously switch from one process to another process. But within the process, again the process itself may transfer the control to different threads. Okay, so that type of multi-threading is what? Implicit multi-threading. But in explicit multi-threading, directly the processor itself is switching. First it executes thread 1 of some process, then it executes thread 2 of some other process, then it executes thread 3 of some other process, so on and so forth. So that is called as explicit multi-threading, which we are going to discuss in detail. Okay. So all commercial processors and most experimental one uses explicit multi-threading. So it allows concurrent execution of instructions from different explicit threads. Right? Interleave instructions from different threads on shared pipelines or parallel execution on parallel pipelines. So how it is done? Explicit multi-threading can be achieved by interleaving instructions from different threads on shared pipelines. Interleaving means what? Interleaving means context switching. Okay, by interleaving instructions from different threads. There are multiple threads, and interleaving means execute one thread for some time, then another thread for some other time, and another thread for some other times. Okay, in shared pipelines. What is meant by shared pipeline? So there is a so it means that we know about pipeline. Okay, we know about pipeline. So in a pipeline there may be what do you call different instructions may be there, right? So pipeline, in a pipeline normally there will be different instructions, and these different instructions may belong to different programs. Okay, so that is what is called a shared pipeline or parallel execution on parallel pipelines. Okay, so or if you have multiple processors, then this can be executed parallelly also. This can be executed parallelly also. Okay, so basically, explicit multi-threading means it is concurrent execution of instructions from different explicit threads. Okay, that is thread belonging to a different process will be a context switched. Okay, whereas in implicit multi-threading, the threads will be extracted from a single sequential program. Okay, so now we are going to discuss in detail about explicit multi-threading. So there are several ways or approaches to explicit multi-threading. What are those? That we will be discussing first. There are basically these four ways. One is called as interleaved. Okay, the other one is called as blocked. And the third method is called as simultaneous SMT. And the fourth method is called as chip multiprocessing. So this interleaved explicit multi-threading is otherwise called as fine-grained multi-threading. It is otherwise called as fine-grained multi-threading. Okay. So it is very similar to a normal multi-threading which we have discussed in operating system. So the processor here deals with two or more thread contexts at a time, and the processor context switching. The processor context switches from one thread to another thread. That is, normally the processor will execute one particular thread during one clock cycle. Okay, switching thread at each clock cycle. Once a particular clock cycle is over, it will switch to the next thread. If a thread is blocked, it is skipped. Okay, so it means that processor, say there are clock cycle 1, 2, 3, 4, so on and so forth. So during clock cycle 1, processor will execute the thread T1. During clock cycle 2, it will execute some other thread T2. During clock cycle 3, it will execute some other thread T3. Okay, during clock cycle 4, it is supposed to execute T4, but assume T4 is already blocked. That is, it is waiting for some IO or something. Then instead of T4, it will execute T1. That is what it says. If a thread is blocked, it is skipped. Okay. So simply how you can understand explicit multi-threading in the sense. Say for example, what do you say? What do you call? Say assume currently the system contains three processes: P1, P2, and P3. Say each of these processes is having two threads. Say process P1 is having the thread T1 and T2. Okay. Process P2 is having a thread T3 and T4. Process uh, P3 is having a thread T5 and T6. Okay. Now with the explicit multi-threading, what happens in the sense, processor knows only about threads. Assume like this. Processor knows only about threads. It does not know about the processes. So totally in the system, how many threads are there? 6 threads are there. Okay, this is with respect to a multi-processing environment. Okay. So there are 6 threads are there. So processor will context switch from, currently we are assuming only one processor, but we may have more than one processor. All those things we will discuss later. Okay. So processor will first execute T1, then for sometimes then it context switch to T2, then it context switch to T3, then it context switch to T4, T5 and T6, so on and so forth. So that type of multi-threading is called as explicit multi-threading. So that is what is called as concurrently executing instructions from different explicit threads. Okay, these are different explicit threads. Okay, right? Whereas in implicit, what happens? Processor context switches only between threads of the same process. Okay, that is called as implicit multi-threading, which we are not concentrating. We are concentrating on explicit multi-threading. So in explicit multi-threading, there are 4 approaches. Interleaved is also called as fine-grained. So here the processor context switches from one thread to another thread. So it executes each thread for a certain duration of time, typically for one clock cycle. After the clock cycle, it will switch to another thread. But during the clock cycle, if a particular thread which is to be executed is blocked, then it will skip that thread. So that is called as interleaved approach. The second is blocked approach. Blocked is also called as coarse-grained approach. Assume that the system contains 3 threads or 4 threads, T1, T2 and T3. Okay, say 3 threads for simplicity. Here with coarse-grained multi-threading, what happens in the sense, processor will execute T1 it will keep executing T1. It won't context switch just like that. It will keep executing T1 as long as T1 does not enter into a wait state. Okay. So it will keep executing T1, but after sometimes T1 may enter into block state because it may want to perform an IO operation, or it may want to fetch an instruction from memory which is not available. Something it may happen, and it may go to a IO or block state. So when T1 get blocked, then the processor will context switch to T2. Then it will keep executing T2 as long as T2 is not going into block state. Okay. Once T2 goes into block state, it will execute T3. So this type of what do you call? This type of multi-threading is called as blocked multi-threading. It is otherwise called as coarse-grained multi-threading. Threads executed until event causes delay. Okay, so as long as there is no delay, so when T1 is getting executed, in between it may create a delay. Delay may happen because of IO operation or any other operation. So whenever there is a delay, then the processor will context switch. Okay. So it is effective on in-order processor. It avoids pipeline stall. Why it avoids pipeline stall? Because if you are context switching at every clock cycle, then at every clock cycle a new instruction should be fetched. Okay. If that new instruction, because at every clock cycle you are moving to another thread. So if that instruction is not in the memory, I mean in the cache, then there will be a cache miss and there may be a stall. Such stalls can be avoided. Okay. Whenever there is a stall, it is going to context switch. As long as there is a stall is what? Delay. Stall is nothing but what? Delay only causes pipeline stall. As long as the pipeline is not delayed, it is going to execute the same thread. But when there is a delay, it will context switch. Okay. So this is the second type of multi-threading, explicit multi-threading. The third is simultaneous multi-threading. So here instructions are simultaneously issued from multiple threads to execute units of superscalar processor. So what is superscalar processor? See, scalar means there is only one processor we have. We have only one processor. Okay. Superscalar means the logical unit of the processor, the single processor can have multiple logical units. Okay. Superscalar means the processor is only one, but it can have multiple logical units. Like it can have multiple execution unit, it may have multiple fetch unit, it may have multiple decode units. Such processors are called as superscalar processors. Okay. Say for example, there is a processor with multiple execution unit. So it has the execution unit E1, it has the execution unit E2, it has the execution unit E3. Then it means what? It can execute 3 instructions parallelly, provided if they are already fetched and decoded. Okay, it can execute 3 instructions parallelly. So such processors are called as superscalar processors. So now this particular processor can simultaneously execute 3 instructions. Okay. So now if you have multi-threading, say for example if you have 3 threads, T1, T2 and T3, now really these 3 threads can be executed parallelly. At a time during one clock cycle itself, T1, T2 and T3, an instruction from T1 and instruction from T2 and instruction from T3, all these things can be executed in a single clock cycle. Okay. So that is what is called a simultaneous multi-threading. Instructions are simultaneously issued from multiple threads to execution units of superscalar processors, because we have multiple execution units. Okay. Right. So this is about SMT. Next is chip multiprocessing. Chip multiprocessing means here really you will have multiple processor. There is only one chip. Processor is normally stored in a chip. We call it as chip. Okay, IC chip. But in this chip there are 2 processors or more than one processor. In a single chip there is more than one processor. So that concept is called as chip multiprocessing. Processor is replicated on single chip. Okay, processor is replicated on single chip. So it only says replicated. We cannot say it's only 2 or 3 or 4. It depends. It varies with architecture to architecture. So minimum there will be two processors. So now we don't have just one processor, really we have two processors. So every unit we have two units, right? So we have two ALU, we have two control units, we have two sets of registers, everything is two. Okay. Each processor handles separate threads. Now if you have two threads, T1 and T2 in the system, then you need not worry anything. Just give T1 to processor 1, T2 to processor 2. Okay. So this is called as what? Chip multiprocessor. Advantage is that the available logic area on a chip is used effectively. Okay. So I think you understand the difference between simultaneous multiprocessing and chip multiprocessing. In simultaneous multiprocessing, there is only one processor, but inside the processor we may have more than one logical units, like multiple execution units. But in chip multiprocessing, we really have multiple processors inside a single chip. Okay, right? So based on this, the approaches to execute multiple threads are classified into these 11 categories. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 categories. We will discuss all these things in detail. First one is a single threaded scalar. So always remember scalar means one processor. Okay, super scalar means one processor with multiple logical units. So single threaded scalar, this is similar to the one which we have discussed. This is very basic thing. This is very basic thing. Like in older days system, if you see, each instruction will be executed sequentially. There is no multi-threading. This is not a multi-thread at all. This method is not a multi-thread at all. Single thread scalar in the sense the processor first executes first instruction. That is, it can execute only one thread at a time. Single thread scalar means it can execute only one thread at a time. There is no multi-threading here. There is no concept of multi-threading. It executes only one thread. After finishing one thread, it will go to the next thread. As long as one thread is not finished, it won't context switch. So that is called a single threaded scalar. Okay. So this diagram shows in each clock cycle there is no context switching. It just executes the same thread, and this thread is waiting for 3 clock cycles. So 3 clock cycle is wasted. Then it is after that it is some IO operations or whatever it has completed. Again it is resuming and continuing. Okay. So this is no multi-threading at all. It is a normal sequential processor without multi-threading, right? Then interleaved multi-threading scalar. Interleaved multi-threading scalar. This is the one which we are discussing in operating system. Here the system can have multiple threads, but these threads will be interleaved. Interleaved means the processor will context switch from time to time. So here if you see the diagram, currently there are 4 threads in the system. These are the 4 threads A, B, C and D. So during first clock cycle, the processor is executing thread A. During second clock cycle, it is executing thread B. During third clock cycle, thread C. During fourth clock cycle, thread D. Again during fifth clock cycle, thread A. Again during sixth clock cycle, thread B. Like that, so on and so forth. After every clock cycle, the processor context switches from one thread to another thread. This is what interleaved multi-threading scalar. Okay. Next is blocked multi-threading scalar. Now also we have scalar. Scalar means one processor. We have one processor. This is interleaved. This is blocked. Now also we have 4 threads A, B, C and D. Okay. So here you see, now blocked we have discussed what we have discussed. As long as the particular thread does not enter into a wait state, that thread will be keep executing. The moment it enters into the wait state, then the controller will be switched to another processor, another thread. Okay. So the processor is executing thread A only. During first clock cycle, thread A. Second clock cycle, thread A. Third clock cycle, thread A. During fourth clock cycle, what happened? The thread A is in wait state. So the processor, one clock cycle it is wasting for thread A. After that, it realizes that okay, thread A is doing some task. It has gone into wait state or something. So it is context switching to thread B. So with blocked multi-threading, the processor will context switch when a current thread enters into a wait state or a block state. Then it will context switch to some other thread. As long as the thread is not entering to the wait state or blocked state, that thread will be keep executing. Okay. So this is what blocked multi-threading scalar. Okay. Next is superscalar. Now we are coming to superscalar. Superscalar means we have one processor, but inside one processor we have more than one execution unit, more than one some logical unit. But let us assume we have more than one execution unit. So remember, superscalar means we have one processor, but inside one processor we have more than one execution unit. We have multiple execution unit. Okay. So this diagram, what it shows in the sense, inside the same processor we have 4 execution units. Inside the same processor we have 4 execution units, which means we can execute 4 instructions simultaneously. We can execute 4 instructions simultaneously. Okay. So, but this is, here we are discussing only single threaded. Here we are discussing superscalar single threaded. We are starting with single threaded. See, this is scalar single thread. So, after scalar single thread, we have discussed interleaved scalar multi-thread, then blocked scalar multi-thread. Similarly, we are discussing now superscalar single thread. Okay, after that we will discuss interleaved superscalar multi-thread. Then we will discuss blocked superscalar multi-thread. Okay, this is the flow. So now we will discuss here superscalar single thread. So now this, even though you have superscalar, but it is going to execute only one thread at a time. It is not going to execute more than one thread. But you have 4 execution units. Okay, remember there are 4 execution units. So there is only one thread. Even you may have more than one threads, but this system cannot execute more than one thread. It can execute only one thread at a time. But it is superscalar, that is it has 4 execution units. So there is only one thread. Thread is what again we call, thread is nothing but a lightweight process, or you have a set of, you have a stream, and the stream is divided into several small streams. These small streams are called as thread. Here we have thread A. Thread A is nothing but what? It is a collection of multiple instructions. A thread is nothing but a collection of multiple instructions. Okay. Here some of the instructions will be dependent on each other, some of the instructions will be independent on each other. Okay, remember this. Here some of the instructions will be dependent on each other and some will be independent on each other. These independent instructions can be executed parallelly. These independent instructions can be executed parallelly. So now we have four execution units. So during clock cycle 1, the processor will try to identify 4 independent instructions from thread A. Because we can execute only one thread. So let us assume we want to execute thread A. So during clock cycle 1, this is clock cycle 1. During clock cycle 1, as we have 4 execution units, processor will try to pick up 4 instructions to 4 independent instructions to execute parallelly. Because if it is dependent, it cannot execute. Say let us assume processor has found only 2 instructions. So it is executing these 2 instructions of thread A parallelly during clock cycle 1. Similarly during clock cycle 2 also processor tries to pick up 4 independent instructions from thread A, but it found only one independent instruction, so it took it and executed. So remaining 3 execution unit is wasted. There is no other option. We are not utilizing it. Then during clock cycle 3, processor tries to pick up 4 independent instructions, but it is unable to find even one instruction. Okay, so it is as if the thread is in the blocked state. Then during clock cycle 4, processor is trying to pick up 4 independent instructions. Now it got 4 independent instructions. All these 4 instructions are not dependent on each other. So it is executing. Okay. Again during clock cycle 5, processor is trying to pick up 4 independent instructions. It couldn't find, so it got blocked. Okay. Again during clock cycle 6, it tries for 4 independent instructions and it got 3 independent instructions and it is executing. Okay. So this is what superscalar with single thread. Okay. Next, superscalar with interleaved multi-threading. Interleaved in itself means context switching based on time. Okay. Right. So here if you see, there are 4 threads: thread A, thread B, thread C, and thread D. Okay. So now what the processor is going to do in the sense, we have, again let us assume we have 4 superscalar, so single processor with 4 execution units, so that the 4 blocks are shown here. In each row there are 4 blocks, so which means that there are 4 execution units available. Now here the processor, how it is divided in the sense, the clock cycle 1 is only for thread A, clock cycle 2 is only for thread B, clock cycle 3 is only for thread C, clock cycle 4 is only for thread D, again clock cycle 5 is for A, 6 is for B, so on and so forth. Okay. So during clock cycle 1, processor tries to pick 4 instructions from thread A, 4 independent instructions from thread A. It found only 2, so it picked that 2 and it is executing. Okay. Right. During clock cycle 2, processor context switch to thread B. So it means in each clock cycle, processor executes only one thread. Thread A is for first clock cycle. Once first clock cycle is over, it switches to thread B. Okay, but we have 4 execution units. So 4 instructions of B can be executed. It tries to fetch 4 instructions from B, but it got only 3 independent instructions, so it is executing the 3. And during the next clock cycle, at the end of second clock cycle, the processor switches to thread C. And again it tries to fetch 4 independent instructions from thread C, but it got only 1, so it is executing it. Then at the end of third clock cycle, it switches to thread D, and it tries to pick 4 independent instructions, and it got 4 independent instructions, and it is executing those 4 instructions parallelly with its 4 execution units. Then at the end of fourth clock cycle, processor is switching to the next thread A, and again it tries for 2 independent instructions. It got 4 independent instructions, it got only 2. Again at the end of fifth clock cycle, processor switches to the thread B, and it tries for 4 independent instructions of thread B, but it got only 1 independent instruction, and it is taking and executing it. So this type of executing is called as what? Interleaved execution. Interleaved execution. Okay. Interleaved multi-threading scalar. Next is blocked multi-threading scalar. So whenever blocked means what? Processor is going to execute only one thread as long as it is not blocked. Okay. As long as it is not blocked. Okay. So during first clock cycle, see here, only when an entire clock cycle is blocked, only when the entire clock cycle is blocked, the processor will switch to another thread. As long as the entire clock cycle is not blocked, it won't switch to another thread. Okay. So during first clock cycle, processor is, we have 4 threads A, B, C, D. During first clock cycle, processor is executing thread A. So it is trying to fetch 4 instructions from thread A, 4 independent instructions from thread A. It got only 2, so it is executing. So but something it got. During second clock cycle also, it won't switch to B because it is what? Blocked multi-threading superscalar. Only when a thread block, then only it will go for another thread. Okay. During second clock cycle also, it is trying to fetch from A itself 4 independent instructions, but it got only 2, so it executes that. Again during third clock cycle, it is trying to fetch 4 instructions from thread A, but it got nothing. So this entire clock cycle is wasted. That is, it got blocked. So only when a complete clock cycle blocked, then only it will try for the, then only it will context switch to what do you call the next thread B. Okay. So next, during the next clock cycle, it is trying to fetch 3 instructions from 4 instructions from thread B, 4 independent instructions, but it got only 3 and it is executing. Next, during next clock cycle, it is trying to fetch 4 independent instructions from thread B. It got only 1 instruction and it is executing. Now here what happens? Thread B is finished executing. There is no more instruction from thread B. So it is so in the next clock cycle, it is context switching to C, because this is the last instruction of thread B. Okay. So with blocked multi-threading, what happens? The processor will context switch only if a particular thread enters into block state or it has completed its execution. So after A, the context switch to B happened because A got blocked during one entire clock cycle. B to C, the switch happens because B has finished execution. So this is called as blocked multi-threading superscalar. Right. So next what we are going to discuss is VLIW. So VLIW stands for very long instruction word. VLIW stands for very long instruction word. Okay, very long instruction word. Right. What does it mean, very long instruction word? In the sense, see, normally one word contains one instruction. In any typical processor, if you take, one word contains only one instruction. So the word size varies from computer to computer. Generally, it will be multiple of 8. Okay. If the word size is 8 bits, that is 1 byte, then each instruction occupies what? 1 byte. If the word size is 1 byte, then each instruction will occupy 1 byte. If the word size is 2 byte, then each instruction will occupy 2 byte. If the word size is 3 byte, then each instruction will occupy 3 byte. Okay. Let us assume that the word size is 2 bytes. In a typical computer, the word size is 2 byte, which means that each instruction occupies how many bytes? 2 bytes. That is 16 bits. Each instruction occupies 2 bytes. Okay. But assume that we have something called as very long word facility. Say the size of this very long is, say the size of the very long is 8 bytes. Say the size of this very long word is 8 byte. Size of the very long word is 8 byte. Okay. But assume that each instruction occupies only 2 byte. One instruction occupies 2 bytes. Okay. And the size of the very long word is, the size of the very long, this is VLIW. The size of the very long word is 8 byte. Okay. So in a very long word, how many instructions you can place? In a very long word, the size of the very long word is 8 bytes. Okay, where each instruction occupies only 2 bytes. So in a very long instruction word, how many instructions you can place? We can place 4 instructions. Instruction 1, we can place. Instruction 2, we can place. Instruction 3, we can place, and instruction 4, we can place. Okay. So totally we can place 4 instructions in a single very long instruction word, because our each instruction occupies only 2 bytes and the size of the very long instruction word is 8 bytes. Okay. So if you have such a facility, then in one clock cycle, we can fetch 4 instructions. This is the idea. This is the idea of VLIW. If you have such a facility like VLIW, very long instruction word, then in one clock cycle we can fetch multiple instructions, because each instruction is going to occupy few bytes, x bytes. But very long instruction word, size of the very long instruction word will be a multiple of x byte. Okay. If the size of the very long instruction word is 4x byte, then in each clock cycle you can fetch 4 instructions. That is the idea. Okay. So let us assume that the very long instruction word, at each clock cycle, let us assume that it can fetch 4 instructions. It can fetch 4 instructions. Okay. And with very long instruction word, now again we will start from the beginning. Single threaded. So this is the flow. Single threaded, interleaved, and then blocked. So we have discussed scalar single threaded, scalar interleaved multi-threading, scalar blocked multi-threading. Then we have discussed superscalar single thread, superscalar interleaved multi-threading, superscalar blocked multi-threading. Now we are going to discuss about VLIW. VLIW single thread. Okay, remember VLIW single thread. Okay. So there is only one thread A. Okay, there is only one thread A. Okay, so processor is what you call? It is fetching. It has to fetch only from that particular thread. Okay. So it is fetching 4 instructions of A, and it is executing. But currently, say only 2 instructions of A is available. So even though VLIW can take 4 instructions, but currently only 2 instructions of thread A are available. Or we need what type of instructions? We need 4 instructions which can be executed parallelly. We need 4 instructions which can be executed parallelly, because here also you should assume that we have multiple execution units. Okay, here also you should assume that we have multiple execution units. It is not single execution unit, we have multiple execution units. Okay, but multiple, even though you have multiple execution units, even though you have multiple execution units, what is the thing? The point is you should get 4 independent instructions. But say at the first fetch you got only 2 independent instructions, then only those 2 are executed. Remaining n represents no operation. Okay, again during second clock cycle, the processor got only 1 independent instruction, so the remaining all are blocked. During the third clock cycle, there is no independent instruction. Okay, so it is blocked. It is blocked. Okay, and during the fourth clock cycle, it got 4 independent instructions. During the fifth clock cycle, again there is no instructions. During the sixth clock cycle, it got 3 independent instructions. Okay, so here the point is, this is also a superscalar with multiple execution unit, but also you have something called as VLIW, which can execute which can fetch multiple instructions simultaneously, because VLIW stands for very long instruction word. Right. Next is interleaved multi-threading VLIW. Okay. So now we have multiple threads. In this first case, we have only one thread, A, B, C, and D. So first clock cycle is dedicated for A, second for B, third for C, fourth for D, and again fifth for A, sixth for B, so on and so forth. During first clock cycle, the processor tries to execute, fetch 4 instructions of A, but it was able to fetch only 2, and it is executing that parallelly 2 independent instructions, and remaining is 2, what do you call, 2 or no operation. Okay, because it has to fetch 4, right? VLIW 4, no, remaining here, remaining 2 will be n. Okay, because no operation, because there is no such instruction, right? Because the size of the VLIW is multiple instructions, right? So during second clock cycle, it has to check in B. It was able to find 3 independent instructions of B. During third clock cycle, it could find 1 independent instruction of C. During fourth clock cycle, it found 4 independent instructions of D. During fifth, it got 2 independent instructions of A. And during sixth clock cycle, it got 1 independent instruction from B. So this is interleaved multi-threading VLIW. Next, blocked multi-threading VLIW. Blocked itself means you should remember what it will keep on execute only one, what do you call, one thread until it went to block state or until it completes. So now also we have 4 execution unit. So we have 4 threads A, B, C, D. So using VLIW, processor tries to fetch 4 independent instructions of A during first clock cycle, but it got 2. Remaining 2 are no operations. During second clock cycle also it got 2 independent instructions of A, remaining 2 are no operation. During third clock cycle, processor was unable to fetch any, A went to blocked state. During third clock cycle, A went to blocked state. A is in waiting state. So this entire clock cycle got wasted. So now the processor is context switching to process B, and it is trying to execute 4 instructions from B, but it got 3. Then during next clock cycle, it tries to execute 4 instructions from B, it got only 1, and B finished executing here. This is the last instruction of B. So now what happens? The processor is context switching from process thread B to thread C. Okay. So this is about blocked multi-threading VLIW. Next is SMT, simultaneous multi-threading. Simultaneous multi-threading. Okay. So this is little different from superscalar. This is also actually superscalar only, but the way of working is different. Okay, this is also, we have only one processor. In SMT also we have only one processor with multiple execution unit. But here the way of working is different. See here in you should understand this carefully. In superscalar and VLIW, if you see, during a given clock cycle, they can execute only instructions belonging to a same thread. They cannot execute instructions from different threads. Say during this clock cycle, they are all are executing only instructions from thread A. Okay, and during first clock cycle, during second clock cycle, they all are executing instructions from thread B. Okay, see this is blocked. Blocked behavior is different. See interleaved. During second clock cycle, they are all executing only B. Okay, I mean in a given clock cycle they can execute only one instructions from only one thread. If you see here, all are A, all are A, all are A, all are A. Okay, here one clock cycle all are A, one another clock cycle all B, all C. In this clock cycle all D, in this clock cycle all A, in this clock cycle all B. This is blocked. Blocked also means what? It will execute A only continuously, then it will go to B or C. So in a given clock cycle, if you see, it is same threads. You take any given clock cycle, it is only one thread will be there. It cannot like one D, A, B like that, it won't come. Okay. So but that is not the case with simultaneous multiprocessing. Simultaneous multiprocessing means in a given clock cycle, simultaneously it can execute threads from, it can execute instructions from multiple threads. Please remember, simultaneous multithreading means in a given clock cycle, it can execute multiple instructions from different threads. In a given clock cycle, it can execute multiple instructions from different threads. I think you got the point. Here you take any horizontal line and you see, it will be from same thread only. All are A. This is all are B. Leave this N. Okay, similarly if you see, this is all are A. This is all are D. Okay, this is all are B. This is all are D. Like that, if you take any line, if you see, it will be from only one thread. But that is not the case in case of simultaneous multi-thread. In a given clock cycle, instructions from different thread can be executed simultaneously. Okay. So here we are considering a multi-thread, simultaneous multi-thread with 8 issues can be given parallelly. Okay, it means we have 8 execution units. 8 issues can be given parallelly means we have 8 execution units. Okay, so these are the available threads A, B, C and D. Okay, so obviously the processor will try to fetch 8 independent instructions from thread A first, but it has not got 8 independent instructions, it got only 4 independent instructions. Okay, no problem. So it took that 4 independent instructions from thread A. Okay, then it is remaining, it has another 4 execution units, right? So it is trying to fetch 4 independent instructions from thread B. It got 3, so it kept that. And there is still one more execution unit. So it is trying to fetch one independent instruction from thread C, so it got it. Okay, this is how it works. So by SMT, simultaneous multi-threading, what happens, we are not wasting this clock cycle, which is getting normally wasted in interleaved multi-threading or blocked multi-threading or interleaved VLLW or blocked VLLW. There in blocked VLLW is N or wasted, right? That wastage will not happen in simultaneous multi-threading. Okay, right? So similarly during third clock cycle also, after C it is trying to fetch from D. Maybe C there is no other instructions, we don't know what. Okay, from D it is trying to fetch during the second clock cycle, as this is the continuation. After C we should go for D. It is trying to fetch 4 instructions from 8 instructions from D, but it got only 3 because now there are 8 execution units are there. So next will be A. So from A it is trying to fetch remaining 5, but it got only 3. Okay, then from B it is trying to fetch remaining 2, but it got only 1. C is finished execution. Okay, C is stopped here. So from D it is trying to fetch one instruction and it got it. Okay, so here C is finished, so there it is going to D. But see the next round, next in the third clock cycle it is trying to fetch 8 instructions from D, but it got 3. Okay, so after that it is trying to fetch 5 from A, but it got 3. Okay, then it is trying to fetch some from B and it got 1 from B. Then again C, maybe previously C is in the wait state if not completed. So again it is trying to fetch from C, it got 1 from C. Okay, so like that, so on and so forth, it continues. So here we are not going to waste any what do you call any issues. These are called as issues. In one clock cycle there can be multiple issues, 8 issues, here 8 issues. Here none of the issues is wasted, you see. But here if you see, in one clock cycle 2 issues are wasted, in second clock cycle 2 issues are wasted, in third clock cycle 4 issues are wasted, such wastage will not happen with SMT. Okay, right. So in SMT also it is only one processor. So all these things we have discussed only one processor, but maybe with multiple execution units up to this 11 techniques. Okay, the last one is actually this is the one with multi-processing, more than one processor, chip multiprocessor. So this is otherwise called as multi-core. Multi-core. So now in one chip we have four processors. So this is one chip. In one chip we have four processors. This is one processor. This is another processor. This is another processor, and this is another processor. Okay. And each of these processor can give two issues. Each of these processor can give two issues. It means each of these processor is having two execution units. Each of the processor is having two execution units. So here we have discussed each of the processor is having four execution units. No, here in one chip we have four processors, and each of the processor can give two execution unit at the same time. I mean two issues at the same time. That is, they have two execution unit. Okay. So these execution unit they work. These are like superscalar, multi-threaded superscalar. So they work in this style. In multi-threaded, they work in multi-threaded superscalar style. Okay. So there are four threads A, B, C, and D. Thread A is given for processor 1. Thread B is given for processor 2. Thread C is given for processor 3. Thread D is given for processor 4. So each of the processor will execute only from this thread. Okay. So processor 1 tries to fetch two independent instructions from thread A, but it got only one. So it is executing, but it got two. So it is executing that two parallelly. It has two execution units. Then during clock cycle 2, it is trying to fetch two instructions from A, two independent instructions, but it got only one. During third clock cycle, it is trying to fetch two independent instructions from thread A. It got nothing, so it is waiting. But now there is no context switch here, because there is only this thread is dedicated for this process. Okay. Maybe if there are more threads, then maybe two threads for one process, like that it may be happen. But as of now, only thread A is for thread A is for processor 1. So it can't do anything. Then also during next clock cycle, it is trying to fetch two instructions, two independent instructions from thread A, it got it. During next clock cycle, it is trying to fetch two independent instructions from thread A, there is no such instructions. Then during last clock cycle it got two independent instructions from thread A, so on and so forth. Similarly for other processes also. So this is actually a true parallelism, because here we have multiple processes. Okay, but even though if you compare performance wise, the performance of SMT is better than the performance of a chip multiprocessor. Okay, because in chip multiprocessor you see, if this clock cycle is wasted means then here it cannot execute B or C or D. That cannot happen. But that is not the case with SMT. SMT is not wasting any issue. See, here it got four instructions from thread A. Then remaining four it can fill up with any other thread. It can take from B or it can take from C or D. But that is not possible with chip multiprocessor. If this is if this is wasted, it is wasted. That's it. You cannot take it from B or C. So this is one of the drawback with chip multiprocessing technique. Okay. So that's it about multi-threading. Okay, and chip multiprocessors. So let us stop here. Fine. Thank you.